Good morning, good afternoon, and good evening to some of you. My name is Dan Ott. I'm the marketing coordinator here at KSPT. Welcome to the Machining High-Temp Alloys webinar. We appreciate your time and your effort today to make it here. Without further ado, I'm going to hand it over to our application engineer, Chris Dixon.
I'll just share it.
Good morning, everyone. Thanks for joining us. As Dan mentioned, my name is Chris Dixon, so I'm the application engineer for SGS's Western region. Been with the company for a little over 2 years now. I support all the states that you see there. Been in the industry for a total of over 16 years now. Majority of that spent in aerospace and firearms. Based out of Fort Worth, Texas. And like I said, I travel around all those states that you see shown there, supporting our sales team and our end users, really diving in deeper into technical applications, testing out tools and different scenarios on the machine, looking at programming, different ways to improve things, and ultimately provide more value at the spindle. So today we're going to be getting into high-temp alloys. So what are high-temp alloys? Also known as super alloys across the industry or various industries. They're going to be grouped up based on what their base material is. If it's iron, nickel, or cobalt traditionally. There's a lot of designer materials out there too, Hastelloy, Wapsalloy, and Kovar. Basically, companies, they'll come up with their own little unique configuration as far as the different alloying elements, and then they'll start building on that, and they'll have all sorts of different configurations from there. They're typically used in applications where you need high strength or corrosion resistance at really high temperatures. You see that a lot in manufacturing jet engines or propulsion systems for space and just really anything where you see a ton of stress and heat applied all at one time. They do have poor machinability across the board, but they can get really extreme to that effect on some of these different configurations. And with that, tooling choices become really critical, and also how you're cutting with them. So there's a lot to kind of unpack there. We'll dive into a little bit of some of the different groups here. So iron-based HTAs. These are going to be your lower cost alternative to your more common nickel and cobalt based HTAs. They are the least demanding of the three. They have the higher machinability. They don't hold up quite as well in some of the extreme temperatures that you'll see the other two holding up well in. But they do always have large amounts of nickel and chromium, so that certainly adds to some of the difficulty in machining them. But across the board, you can usually kind of equate them to a austenitic stainless. So probably the most common you'll see out there is A286. You also see N155 or CG27. Next up, we have the nickel-based. This is what you're usually going to see the most of. They are large amounts of chromium mixed with nickel. Strength is really high at high temperatures, very corrosion resistance. You have better luck machining the heat treated versions or solution treated versions. And there's a lot out there. There's all sorts of different brand names and different alloys that all have different machining properties because of their mechanical properties. So 625 Inconel and 718 Inconel are some of the things that you'll see most often. You also see Rene 150 or Wapsalloy or Hastelloy. There's just, like I said, this is a really wide group. Get rid of that. Next up is the cobalt based. So this is I won't say obscure, but you just don't see cobalt alloys quite as much. And that's a lot to do with the fact that they have a very low machinability, even compared to the nickel based stuff. There's also more expense involved in there typically, but they do hold up very, very well under high temp operations. But you'll also see it a lot in medical. Cobalt chrome alloys are very, very heavily used in the medical industry. And at the end of the day, this is like I said, the most difficult to machine of the three. They tend to work harden very quickly, and they operate at very high temperatures on the cutting edge, so they can be very brutal on tools. Common examples are stellite, the cobalt chrome molybdenum, and then L605. So when machining HTAs, it's no different than anything else. Ultimately, machining is just making chips. To make a chip, you need heat, or you need tool pressure and a tool, and that generates heat. You can see in the diagram, the different fluctuations in temperature from the very cutting edge on the tip, going up the flank or inside the rake of the tool. Uh, this is what we're managing. Machining efficiency is basically managing that heat and that pressure. And you do that by changing the geometry of the tool, adding coatings, obviously applying coolant and or lubricants, and by using different cutting strategies. And with HTAs, you need even more heat, or you generate more heat because you need even more pressure to make a chip. And that's really where the difficulty that, the headache that people generally associate with machining HTAs come from. So we manage that a lot by tool geometry. There's a lot of different geometrical features on the tool that we can tweak or modify to get more efficiency in that cut. The two primary are your radial rake angle and your helix angle. So radial rake is going to play the biggest role in metal removal. So by changing the radial rake, we can change how that chip forms off the edge of the tool. And we kind of play a game of balancing between the power, the actual cutting power required versus that edge strength. So by going with a more positive rake, it produces the chip a little bit easier. It's a sharper edge, but it doesn't have the same rigidity there. And you can see that space kind of behind the cut here. That's going to add a little bit more fragility into that edge, as opposed to going to more neutral. That angle lowers, and then going into a negative. Now you have a lot of material behind that edge, so it just adds to the strength of it. But as you go more negative, you require more horsepower, more force behind that cut, which in turn does increase the actual cutting pressure. So your tool needs to be able to handle it, your machine needs to be able to handle it, and your work holding needs to be able to handle that. Next up is helix angle. So helix angle helps with getting the chips up and away from the cut, and also helps with the shearing action of that tool. Now shearing, a lot of times you think about aluminum, like, we really want to get a good shear there because, we're going to get a better finish, and, it's going to make it cut real easy and pull that chip away. Well, on HTAs, shearing can be a big benefit as well, because they are increased shear can be a big benefit, because traditionally HTAs don't like to produce a chip. They tend to be, real dense and gummy, and they don't like to just pop a chip off at will. So increasing shear can help with that, especially when it comes to finishing. The degree of your helix will also determine how those chips are evacuated and what the contact with the workpiece is. So with a tighter helix, you're going to have more contact, which is ultimately more drag, and also more heat generated as well. So those are things to kind of be mindful of. And you can kind of see the little graph down here. As you change that helix, you get more shearing action as you go to a tighter helix. As you go down, you get less chip flow, but you get a more rigid tool. So, there is a balance and a trade-off there. And, you have to kind of look at what your application is, what your material is, and how you can best benefit from that. The other factor is the two combined together, your helix angle and your radial rake, actually gives you a effective, or what we refer to as a dynamic rake. So by combining those two angles, you actually can get a what's more of a effective cutting angle. So if you take a 5-degree rake and a 30-degree helix, and you have an effective rake of 17.9. Now you take that same 30-degree helix and add a 10-degree rake, and now that jumps up to 21. And it multiplies up from there. So this allows you to take a tighter helix, put in a lower rake, but still get a good shearing effect. So you make a really robust edge, and you kind of get a good balance between the two without having to go to a completely sharp tool. So again, this is kind of trying to find that best of both worlds, but also providing a very effective solution with a tool. And we utilize this a lot through our product line. So the next geometrical features are relief type and then the flute count. So the relief plays a really big factor when it comes into HTAs. The two common types that you'll see are your eccentric relief and your faceted relief. So the relief is really providing you a couple of things. It's going to give you stability and durability in your cutting edge, but it can also increase the contact with the material, create more heat, more drag, and it can add to your cutting forces. So you have to kind of have a little bit of a balance there, and you need to look at what your tool is being utilized for as to which types of reliefs that you want to go with. With the eccentric relief, it's a radial grind. It kind of has a sloping drop off. So you have more material right behind your cutting edge, going back to like the rake angle. This makes just a beefier edge that's going to hold up better under high load and high pressure and also high heat. The faceted relief is a double grind, traditionally a primary and secondary, and so it drops off from the edge quickly and then it drops off even more from there. This is going to produce a really sharp edge that will help you get a really good finish, but you just don't have as much meat behind that edge right there, so it is more fragile. So again, it depends on what you're trying to do as to which one may be better suited for what you're doing. Flute count, same thing. Flute count plays a big factor as far as your chip space. And so you can see down here different depictions of higher going from a 2 flute up to a 6 flute. You can see how that chip space decreases as we go through there. So ultimately, that's going to affect your step over. It's also going to affect the rigidity of the tool. So the higher your flute count is, traditionally, the larger your core diameter is, which means you have a more rigid tool. It tunes out harmonics better. You get less chatter. And overall, it's just a more solid tool. It also allows you to go faster. You have more flutes. You can push your inch per minute, your surface footage some. But lower flute counts can be better for aggressive tool pass. So if you're trying to do like a full slot, or you want to do a constant step over where you're doing a medium to a heavy step over, then you don't want to have a really high flute count tool because you're not going to be able to handle that chip that's going through there. So, these 3, 4, even 2 flutes for certain materials are just a better option there. Now, with high temp alloys, you're not going to be pushing these aggressive chip loads typically. So you can get away with a higher flute count in some scenarios that you might not get away with on, say, a traditional stainless or especially like an alloyed steel or something like that. Again, you have to take into account the entire body of work. What are you doing? What's your entire setup? And how do these all kind of play in together? Next is coating, and this is extremely important when it comes to high temp alloys. The coating is essentially providing a multitude of things. It's making the surface of the tool harder, which helps with the abrasion and wear, which is extremely high on most high temp alloys. It also protects the substrate. It stops or prevents the material from adhering to the substrate and then peeling it away, ultimately removing some of your actual cutting edge and making your tool break down. In most cases, it increases your lubricity, and most importantly, it provides a thermal barrier. And in high temp alloys, that is probably the biggest factor aside from the wear resistance. There's a ton of heat that's generated in that cut, and your coating is really going to help fend that off. It's going to spread that heat out across the coating instead of allowing it to centralize in that cutting edge. Because high temp alloys, the whole purpose of them is that they can handle high temperatures. They have low thermal conductivity. So that heat really stays centralized right there at that cutting edge. So with an uncoated tool or, with the wrong coating, that builds up right there at that cutting edge and ultimately that edge is going to wear down and break down much easier than that workpiece material is going to, because that's what it's designed for. So you could see here's a demonstration of a coated versus an uncoated tool. Uncoated on the left, coated on the right. And you can see that the uncoated or the coated tool is going to be uh, you'll see a buildup of heat faster, but that's what's happening there is that, like I said, that coating is spreading that heat across the coating itself, whereas in the uncoated tool, it's building up solely around the edges. And this one's going to reach a certain point, and it's not going to get much more hot or much hotter from there. Whereas these edges are just going to continue to get hotter and hotter and hotter until eventually they break down, or the cut itself ends. So there's a drastic difference in how these tools handle that heat. And in HTAs, again, that's extremely critical, because ultimately that's just going to equate to better tool life, lower cost and overall tools, and also preventing potential scrapping of parts from a tool failing in the cut. So coatings are a huge factor. Next up is tool paths. So tool paths, I think, kind of gets overlooked in a lot of cases as far as how I'm choosing them based off the materials that we're cutting. A lot of people look at it and say, okay, well, I have these tool paths available, so I'm just going to use it. But there is some considerations to have. Part geometry definitely plays a big factor into it. What tool paths you do have available in your CAM software. Obviously, you can't use something that you don't have. But your high efficiency milling or machining, or high speed machining, dynamic mill, adaptive mill, whatever you want to call it, or trochoidal tool paths, they use constant cutter engagement. And that's really beneficial when it comes to HTAs. We've talked about the heat and the pressure generated in those cuts, and with a constant step over, where the tool is going in 70 thousandths or whatever, and it's staying there, and it goes straight in and goes straight down the tool path, you're generating heat from the moment that tool enters to the moment it exits. And whenever you have spikes in your tool engagement, that can be really detrimental to your tool. So by going to a constant engagement instead of constant step over, you can really control that engagement. Well, you're obviously controlling it, but really you're controlling that heat and that buildup of pressure and preventing those spikes in that. And so here you can see a demonstration of the two. So on the left, we have a constant step over, and you'll notice every time it hits one of these corners, it does a full slot in there. And so unless you have a really low flute count tool that's really rigid and your rates are correct, it's not going to survive that in a high temp alloy at all. Whereas on this, we have a constant cutter engagement. I'm going to back that up some. So you can see each time it's coming across, it's doing the same 10% step over, and it's arcing into the cut instead of just driving directly into it, spiking that tool load. And overall, it's just a much more gentle, more efficient operation for the tool, the workpiece, the spindle, the axis on the table, everything. So, it's just a better way to control the tool. Now, they're not always the best tool paths. Sometimes if you need to run a slot, and it's a simple feature, then it is best just to run a traditional slot straight down there. You need to have a tool that can handle it. Your rates need to be appropriate, but you can get through there a lot faster. And ultimately, if everything is set up properly, you'll probably end up getting a little less tool wear in the long run that way. So again, with everything, there's 1,000 ways to skin a cat. There's not always a right way or a wrong way. There's just sometimes a better way. And sometimes constant engagement is better, and usually it is, but occasionally you'll find situations where a constant step over is just a better overall tool path. So tool engagement, what does that really look like? So here on the left, you'll see your radial width of cut. So this is your radial step over. As your step over increases, that tool engagement increases as well. So, this is a 10% cut, a pretty small angle of engagement there. Now we get to a 50%, and we have a much a more significant portion of the tool engage, this is going to be higher load on the tool, higher load on the part. Your chip load is going to be higher. It's just ultimately it's just stress on the tool. Then we get into a full slot, and now you have a full 180 degrees of engagement here. So there's again heat and stress that's building up there. Now, if everything is correct, then you have a tool that can handle it. It's no big deal, but you have to account for those things. And sometimes this is also controlled by the tool path. So on the right-hand side, you'll see that these are all a 10 or 15% step over. And as you go on a straight path, you have minimal tool engagement. Then when you go into this inner curve, you have much higher tool engagement. And then when you switch to this outer curve, you have a significantly lower tool engagement. Now, if you're running at the same parameters, your same inch per minute, same chip load, for all of them for this, when you get here, now your tool is going to bog down because it's got a much higher engagement, and it's not your parameters aren't set to be prepared for that sort of engagement. And inversely, when you come out here, your parameters are going to be too low. You might get some chatter because your tool's just not engaged as well. If you have a really large diameter tool, then you may only have one or two flutes engaging, so you're just not getting good contact with the workpiece. So these are all things that you have to look at and really kind of dial in for your specific application. So what's the right tool? It's an HTA. It's going to wreck my tool no matter what. It doesn't matter what I throw in there. Well, that's not wrong, but ultimately high wear is expected. But there is a right tool for the job. Are you doing a heavy radial step over? Are you doing high efficiency machine? Are you roughing? Are you finishing? Do you need a long length tool? Do you need a stub? Do you need chip breaker or continuous edge? Can you get away with flood coolant, or do you have internal coolant as an option? These are all things that you have to consider when you're looking at how you're approaching your job. Sometimes you may not have that option. You might just have a tool that's there, and this is what you got to do to get the job out the door. So then you're going to go back and tailor what we just talked about to kind of suit your tool and your workpiece. So it is an overall process, and there's a lot that goes into it. It's not just slapping a tool in there and saying, well, I'll replace it when it breaks, because it's going to break anyways. It's an HTA. And there's a lot out there. So what best suits your application? So within our product line for HTAs, we have a lot of options. Some specifically designed for HTAs, and some that are just very well suited for it, and also well suited for different types of operations. We have our T-carb 6 flute, the V-carb 5 flute, multi-carb, our Series 77 H-carb, the HPR, and our Z-carb HTA, and then the Series 33. We'll dive into a little bit about each of those. So for roughing options, these are things where we're doing traditional tool pass, constant step over, heavy to moderate radial step overs. We have our Z-carb HTA. So this was a variation off of the original Z-carb that is specifically for high temp alloys. It's 4-flute variable index. It also has variable helix, so it really helps with chatter. It does have positive rake angle, so you get good shearing effect there. And because it was specifically designed for HTAs, it has a heavier core, so that makes it a more rigid tool. It makes it hold up to those stresses of the cut more effectively. A lot of size options. You can get a weld and flat, and it does come with Dynamite A coating, which is one of our coatings that is well suited for high temp alloys. The Series 33. So this is a 3-flute option. And most people, whenever you think of 3 flutes, you think of aluminum tools. But this was specifically designed for stainless steels and high temp alloys. It has a variable helix. It goes from a 32 up to a 48-degree helix. So it has the most amount of chatter prevention built into the geometry of any of our tools. It also has a stepped core, and you can see that right through here. So the core diameter changes as it goes down into the flutes. And ultimately, that just provides a lot more rigidity into the tool. Again, lots of size options, and it does come with that Dynamite A coating as well. My opinion, this is one of the more underutilized, if not the most underutilized tool in our portfolio. It's a great tool, especially if you're doing tight pocketing, something where it really needs to dig into a corner. That 3 flute design really helps cut down that stress and load from less contact with the workpiece there. So you get into a high flute count tool and you try to dive it off into a tight corner, you're going to get chatter. That tool is going to want to bind up a little bit because that engagement is spiking as it gets in there. And this tool really combats that very well. So our more hybrid into HEM options. So we have the Z5 or Z-Carb HPR. This is what I consider our general purpose high performance tool. It does a little bit of everything and it does most of that very well. It's a 5 flute tool with variable indexing, has a 37-degree helix, and it does have through coolant options. So if you're pocketing, doing anything internally with high temp alloys, this really helps with that. Has a lot of options as far as fractional and metric sizes. You can ramp with it. You can also get pretty aggressive with your slotting. So this is that tool that really kind of fits the widest band of options as far as applications goes. We can go from slotting down to finishing with it. You just got to make sure you have the right parameters and the right setup to be able to handle whichever side of the spectrum that you're going with. Next up is the T-Carb. It's a 6-flute tool with variable index. It has a higher helix at 41 degrees, but it does have a little bit lower positive rake. So it has a nice robust edge. That helix helps with shearing, which is great for high temp alloys. It is center cutting. We have a lot of options for diameters. We also have neck options. So if you need to get down in, get some reach on something, this is a good tool to look at for that. It comes in our Dynamite X coating, which is also very well suited for high temp alloys. And we also just released a ball nose variation of this. So the ball nose has a little bit different geometry on it, a little bit slower helix, but the end work on it is very well suited for high temp alloys. We're really excited about this expansion of this tool line. And it is focused towards the titaniums and high temp alloys market. So a lot to be said about the T-Carb. It's a great tool for high temp alloys, especially if you're looking for some of the different variations that are offered within that portfolio. The Series 77, the H-Carb, this is an incredible tool. We released it a little over a year and a half ago, and we've just had nothing but great success with it, especially when you're trying to get into deeper axial engagements. This is the go-to tool for that. So it's a 7-flute design with variable indexing. It has a 37-degree helix. You can get it in a 2.5, a 3, or a 4 times D length of cut. So very helpful for your true HEM operations where you want to try to get that 10% step over maximum flute length. We can run up to 4 times D at 10% with pretty much any material. It is a chip breaker tool or a continuous edge tool, so you have that fluctuation there. Chip breaker definitely helps with lowering that stress on the tool, getting smaller chips, making them easier to evacuate, especially those really dense and heavy high temp alloy chips. So a great option there. Lots of sizes, lengths, corner radiuses, and it does come as one of the options at Dynamite A coating, which is, again, well suited for HTAs. Again, just a great tool, especially if we really want to try to maximize that material removal rate. Get that, lower to light radial, high axial engagement, and really increase those feeds and speeds. So finishing, we have 2 different options that are well suited for finishing. Now, this is where people say, oh, well, I don't want to have a specific finishing tool. And you don't have to. All the tools that I previously mentioned, you can finish with those. You just have to have the right rates. And you have to know if you've been roughing with it already that your edge may not be as sharp. You may not have the shear factor there to get the best finishes out of them. So even then, you still may want to put a new tool in for finishing and then let it wear a little bit and make it a rougher or whatnot. But as far as dedicated finishing options goes, these are 2 great options. So the V-Carb, it's a 5-flute variable index, 45-degree helix. Does have a high positive rake. So between the two of those, a lot of shearing action there going on. So it's great for finishing, especially these materials where they don't want to make a chip. If you're taking a light step over, that sharp edge really helps with producing a chip and getting a higher quality finish instead of just kind of rubbing across the top of the material. With that, though, you do have a more fragile edge. So in these types of materials, traditionally, I would say you want to stick to finishing operations. You can get into semi-profiling or semi-finishing, but for the most part, I would stick to finishing here. Again, lots of options as far as sizes goes. Weld and flat does come with that TA coating. The other options are multi-carb. This is, again, a dedicated finishing tool. 7, 9, or 11 flutes, depending on what your diameter is. So, as we get larger, get up to that 11 flute count, we can get some really good rates out of it, even at really light finishes. Very helpful as far as productivity goes. It has a 35-degree helix, so a little bit slower helix, but it does have a nice sharp edge to it. With that flute count and that helix, it has the largest core diameter of any of the tools in our portfolio. So very rigid tool. Excellent for trying to finish parts that require very exact perpendicularity between a wall and a floor. Very good for resisting chatter. Just all around, it's just a great tool for finishing. And going back to kind of what I was saying earlier about chip space, with the lower chip loads on HTAs, you can get away with some more aggressive step overs. 3, 4, 5, 6% potentially with this type of tool. Again, that's going to come down to your specific application. It's not something I would just throw in and see what happens. But everything, there's always something that you can try. You can always do something differently. That's one of the things I love about my job is you get to go into different places and see things that you may have previously thought not possible, and someone's sitting there doing it all day long, and they're incredulous as to why you think that it shouldn't work. So at the end of the day, you can do a lot with a variety of tools. And so just because we say something is a finisher or a rougher, that doesn't exclude it from doing other things. You have to figure out what's best suited for what you're doing. So from a troubleshooting standpoint, we've looked at a lot of tools, different ways to implement them, things to consider. So now when you're using them, what are you looking for? So if you're seeing flank wear, anything like that, the biggest culprit there is going to be heat buildup. You're getting too much heat on that edge, and it's just causing that edge to erode away essentially. So you want to look at lowering your RPM, increasing your feed rate, doing something to try to get that heat off that edge, pull the heat away in the chip. If all of that's dialed in, then it could be a coolant thing. Getting more coolant to the cut, checking your concentration, or even checking to see if you have the right coating. There may be a better coating that's suited for that material. The other thing is corner chipping. And this will generally come from your feed being too high. You might have a tool that's just too sharp for what you're trying to do with it, or you don't have the right rigidity, whether that be in the tool holder, the work holding, the machine. You may just have if you have an old beat up machine that's still chugging along though, if you have real fragile edges on your tool, they might break out more easily. You might need to go to a more robust tool to be able to handle some of that potential looseness or lack of rigidity in the machine. But you can play with your RPMs. You can go down to, increase the corner radius, add a chamfer, anything like that to help beef up that edge. Chatter. Ultimately, this is generally a tool path thing. So either your speed is too high, the tool is pushing, it's not cutting. So you may have the wrong engagement angle for what you're trying to do. Your tool may not be well suited for it. You may have a tool that's really robust, but has a kind of a rolled or honed edge, and you're trying to take a light cut. So it's not getting underneath that material and really removing it. Your setup could be a problem. You may have a weak tool holder where you're trying to take really heavy cuts and your tool's essentially bouncing against the workpiece, or vice versa. Your work holding may be weak, or your part, if you're machining a thinner wall and you're trying to get aggressive, your part could be bouncing against your tool. So lot that could be there, but generally it comes into playing with feeds and speeds and really getting it dialed in for your particular workpiece and machine environment. Edge cratering, generally that's caused by your speed being too high. You could have too high of a relief. No coating will certainly play a factor in that, especially with HTAs. The abrasiveness and the heat generated from those materials will just run across that edge, and it'll cause them to crater out, which will ultimately break down that edge and cause it to break out and chip away. Again, edge chipping, kind of alluded to that just then. There's a lot of factors that can go into edge chipping. Having run out in your tool is one. Not having rigidity in your setup, you're getting chatter. So now that tool is overloading and underloading depending on how that chatter is bouncing there. And that can cause your edges to chip out. Also vibration, having too high of a feed rate, it just puts too much stress on the tool. Again, there's just a lot of things there. So, look at your fixturing, your setup, check the tool for run out, play with your feed rates, drop it down a little bit, see if that edge holds up better. But ultimately, you're just really looking at how can you lower the stress on that tool. That's generally the cause of cutting edge chipping. And then catastrophic failure. The tool just blows up. I mean, if you've been doing this any amount of time, we've all had it happen. It's going to happen again. Um, there's a lot of causes of it. You can have chip packing, recutting of chips. That's a big factor, especially with high temp alloys. If you're not getting those chips out and away from the cut, and that tool is trying to cut chips and workpiece at the same time, it's going to cause those edges to break down really quickly. The tool's going to start pushing. It's going to spike the pressure, and that tool is going to pop, or your piece is going to move, and then you got a lot of problems going on at one time. Um, but chip packing, excessive wear, if that tool's again worn out, it's pushing, it's not cutting, it's going to blow up. Not getting enough coolant into the cut, same thing. It just gets hot, wears down quickly. Now you're pushing and not cutting. You can kind of see a pattern here. Ultimately, a lot of times a tool blowing up is because it starts pushing material and not cutting it. And in these types of materials, a lot of times that tool is going to give before the material does. So, there's a lot to diagnose when that happens, especially on smaller tools. You're not necessarily going to be able to see some of these factors beforehand. So you kind of have to be aware ahead of time and plan for them and make sure all your I's are dotted and your T's are crossed. And that's it. That's a lot in a small package there. And I went through some of it a little bit fast. Some of it you've probably seen before if you've attended my previous seminar. But at the end of the day, machining high temp alloys is not that much different than anything else. You just have a smaller window of error. You have to think about things a little bit ahead of time, plan for that heat, that pressure, and make sure you have the right tool for the job. So with that, I'll turn it over to Dan.
Thanks, Chris. So like you guys can see on the screen, my name is Dan Ott. I am the marketing coordinator here at KSPT. I've been in the marketing role for roughly 5 years, 15 years total with SGS, based right here in Cuyahoga Falls. And I handle all of the company's external communications, whether that's social media, the website itself, our e-newsletter that goes out quarterly, the digital catalog, and then the tool wizard as well, which I'm sure you guys are all familiar. And if you're not, be sure to visit our website and check out any of those things I just mentioned. A lot of great content.